Welcome you all. In this session, we will discuss some numerical based on vapor compression refrigeration system. This is the first numerical. In a VC system cycle, the following are data obtained. The enthalpy at inlet to compressor is 180 kJ. The enthalpy at exit to compressor is 210 kJ. The enthalpy at an exit of condenser is 80 kJ. Then COP of the system. You have to find the COP of the system. Okay. Right. This is in this figure. The VS cycle is shown on TS plot. In this question, the following data are given. The enthalpy at the inlet to compressor. Since compressor is installed between 1 and 2, therefore point 1 is the inlet point of compressor. So enthalpy at the inlet of compressor, that is H1, is 180 kJ. Enthalpy at the exit of compressor, that is 2 is the exit point, therefore H2 is equal to 210 kJ. The enthalpy at the exit of condenser, since condenser is installed between point 2 and 3, and the enthalpy at the exit of condenser, that is S3, is given 80 kJ. Since we know that the process 3 to 4 is the throttling process, in this process enthalpy remains constant, therefore S3 is equal to H4. So S3 is equal to H4, this is equal to 80 kJ. Now we have to find the COP of the system. We know the COP is equal to refrigeration effect by work input, and refrigeration effect is equal to H1 minus H4 because the evaporation is responsible for refrigeration effect. So this refrigeration effect is equal to H1 minus H4 and work input is equal to H2 minus H1. Okay, so this is refrigeration effect, this is H1 minus H4 by work input, this is H2 minus H1. The H1, since we know that S3 is equal to H4, so this H4 can be replaced by S3. So this is equal to H1 minus S3 by H2 minus H1. All these values are given in question. Simply we have to put the value and we will get the result of this one. That's the COP is equal to 3.3. Now let us move to the next question. In a 5 kilowatt of cooling capacity refrigeration system operates on VC cycle. A 5 kilowatt of cooling capacity refrigeration system operates on VC cycle. The refrigerant enters the evaporator with an enthalpy of 75 kJ and leaves with an enthalpy of 183 kJ per kg. The enthalpy of refrigerant after compressor is 210 kJ per kg. Then calculate the coefficient of performance, power input to compressor, rate of heat transfer to condenser. Right? This is the problem. Okay. This is the solution of this problem. So this refrigeration system works on VC cycle, and in this question the refrigeration effect, the cooling capacity of this plant, that means this is refrigeration effect in kilowatt. The cooling capacity of plant is given, this is 5 kilowatt. That means the refrigeration effect in kilowatt, this is equal to 5 kilowatt. The refrigerant enters the evaporator with an enthalpy of 75 kJ. We know that this evaporator is installed between 4 and 1. Therefore, the enthalpy of refrigerant at an entry of evaporator, this is H4, is equal to 75 kJ per kg. Enthalpy at exit of evaporator, since point 1 is the exit point of evaporator, this H1 is given 183 kJ per kg. And enthalpy at an exit of compressor, this compressor is installed between point 1 and 2, and this point 2 is the exit point of compressor. Therefore, this H2 is equal to 210 kJ per kg. So these data are given. Now you have to find the coefficient of performance, power input, heat rejected by condenser. Right. First of all, we know that the COP is equal to refrigeration effect by work input, and refrigeration effect is equal to H1 minus H4. and work input is equal to H2 minus H1. This all values are given in question. Simply we have to put the value of H1, H2 and H4. You will get the COP of the plant is 4. Right. Since we have to find the power input in kilowatt, therefore we need to find the mass flow of refrigerant. For this purpose, since this refrigeration effect in kilowatt, this is the cooling capacity of plant. This is refrigeration capacity. This is given in 5 kilowatt. So this refrigeration effect in kilowatt, this can be written this m dot into H1 minus H4. Okay. So m dot is the mass flow rate of refrigerant and H1 is the enthalpy at an exit of evaporator and H4 is the enthalpy at an entry of evaporator. So simply we have to put this value. The refrigeration effect is given, H1 and H4 are given. After putting the value, you will get m dot. This is mass flow of refrigerant. This is equal to 0.0463 kJ per kg. So this is mass flow rate of refrigerant. Once we have find out this mass flow of refrigerant, then we can find power input in kilowatt. This power input, that means this power input, this is required to run the compressor. This power input, this power is required to run the compressor. This is equal to mass flow rate m dot into H2 minus H1. Okay, because this compressor is installed between 0.1 and 2, therefore this power input is equal to m dot into H2 minus H1. This is equal to this mass flow rate is given, H1, H2, all terms are given. Simply we have to put the value, we will get power input is 1.25 kilowatt. In third bit, we have to find the heat rejected by condenser in kilowatt. Since heat rejected by condenser, right? This condenser is installed between 0.2 and 3. Therefore, this heat rejected by condenser is equal to m dot into H2 minus H3, where m dot is the mass flow of refrigerant which we have calculated. This m dot is 0.0463, H2 is 210 kJ per kg, H3 is 75 kJ per kg. After putting this value, we will get the heat rejected by condenser is equal to 6.25 kilowatt. Well, this is the next problem. In a simple VC cycle, following are the properties of refrigerant at various points. At compressor inlet, this is H1 is equal to 183.2 kJ per kg. A specific volume at compressor inlet is 0.0767 meter cube per kg. The compressor discharge, this is H2, enthalpy at compressor discharge is equal to 222.6 kJ per kg, and this specific volume is equal to 0.0614 meter cube per kg. Okay, this is the enthalpy and specific volume at compressor discharge. At condenser exit, this S3 is 84.9 kJ per kg and specific volume V3 is 0.00083 meter cube per kg. In this question, the piston displacement volume of compressor is 1.5 liter and its volumetric efficiency is 80%. Then we have to find a speed, and this speed is also given, this is 1600 rpm. So we have to find the refrigeration effect in kilowatt and power input in kilowatt to run the compression. Okay, so this is the problem. This is simple based on this problem based on VC cycle. Okay, so this is the plot of the VC cycle on TS plot. In this numerical, this H1 is given 183.2 kJ per kg and a small V1 a specific volume, this is 0.0767 meter cube per kg. This H1 is the enthalpy at an entry of compressor and small V1 is a specific volume of refrigerant at an entry of compressor. H2, this is a specific enthalpy at an exit of compressor, and a small V2, this is a specific volume at an exit of compressor. S3, this is the enthalpy of refrigerant at an exit of condenser, this is 84.9 kJ per kg. A small V3, this is a specific volume at an exit of this condenser, this is 0.00083 meter cube per kg. The piston displacement volume is given 1.5 liter. Since we know that 1 liter is equal to 10 to the power minus 3 meter cube, so that's why this piston displacement volume can be written 1.5 into 10 to the power minus 3 meter cube. The specific volume is 80%. Then the speed of this compressor is given 16 rpm. Then we have to find the refrigerant effect in kilowatt and power input in kilowatt, right? Okay. First of all, we know the volumetric efficiency is equal to, this is the basic formula of volumetric efficiency of compressor. It's m dot into V1 by pi by 4 dA square ln This m dot is the mass flow rate of refrigerant. A small V1 is the specific volume at an inlet to the compressor, and this dA square, this d is the bore of this compressor, L is the length of the stroke, N is RPM, and K is the number of cylinders, right? This is the basic formula. We have explained this formula in our theoretical part. In this formula, the specific volume V1 is given. Okay, this is what is this V1? V1 is the specific volume of refrigerant at an entry of compression, right? And one important thing we have to be careful, this pi by 4 d square L. Basically, this is the swept volume. This is the swept volume of this compression, right? This pi by 4 d square L, this is the swept volume of this compressor. This is piston displacement volume. This term can be represented as piston displacement volume of compression. This value is given 1.5 liter. This 1.5 liter means 1.5 into 10 to the power minus 3 meter cube. So pi by 4 dA square L is piston displacement volume. This is given 1.5 into 10 to the power minus 3 meter cube. And this N is RPM. This we will convert in RPS because this is rotation per minute, right? And K is the number of cylinders. Since this compressor has single cylinder, there is no information regarding this number of cylinder. That's why you can assume that number of cylinder is 1. So volumetric efficiency is given 0.8. This is equal to m dot into a small v1 is 0.0767. This swept volume is pi by 4 dA square L. This is equal to 1.5 into 10 to the minus 3 meter cube. And this N is 1600 by 60 rotation per second. And number of cylinder is 1. If you put this value, you will get mass flow rate of refrigerant. This is the mass flow rate of refrigerant. This is equal to 0.417 kg per second. From the concept, the formula of this volumetric efficiency, we have calculated the mass flow rate of refrigerant. This is equal to 0.417 kg per second, right? Now we have to find the refrigerant effect in kilowatt. We know that this refrigerant effect in kilowatt, this is equal to m dot into H1 minus H4, because this refrigerant effect is occurred by the absorption of heat by evaporator. Therefore, this refrigerant effect m dot into H1 minus H4. This m dot is given, we have calculated, this is 0.417 kg per second. H1 and H4 is H4 is equal to S3 because process 3 to 4 is the throttling process. Enthalpy will remain constant. Therefore, this H1 is equal to 183.2 and this S3 is equal to H4. This is equal to 84.9. If you put the value, you will get refrigerant effect is equal to 41 kilowatt. So refrigerant effect will be 41 kilowatt, right? We have to find the power input in kilowatt. Since power input is this power input required to run the compressor, and compressor is installed between 1 and 2. Therefore, this power input will in kilowatt. This is equal to m dot into H2 minus H1. This m dot we have calculated. H1 H2 we know. Simply we have to put the value. You will get power input is 16.43 kilowatt, right? So this is the one important problem we have solved this one. Right. This is the next problem. A refrigerator based on VC cycle operates between the temperature limit of minus 20 degrees centigrade and 40 degrees centigrade. The refrigerant enters the condenser as saturated vapor and leaves as saturated liquid. The enthalpy and entropy values of saturated liquid and saturated vapor at this temperature are given in this table, right? In this table, this temperature is in degree centigrade, is HF, HG, SF and SG. These are given at this temperature, minus 20 degrees centigrade and 40 degrees centigrade. These values are given. So we have to find the COP of the cycle. Right? Next bit, if refrigerant circulation rate is 0.025 kg per second, then find the refrigeration capacity in kilowatt, right? Okay. Okay, so in this problem, first of all, we need to understand the problem. A refrigerator based on VC cycle operates on the temperature limit of -20 degrees centigrade and 40 degrees centigrade. That means this VC cycle operates between -20 degrees centigrade and 40 degrees centigrade. This -20 degrees centigrade is temperature of evaporator and this 40 degree is temperature of condenser. Because we know that this VC cycle, this compressor and this evaporator and condenser, this evaporator works at lower temperature and this condenser works at high temperature. So this temperature limit is -20 degrees centigrade and 40 degrees centigrade. That means this TL is lower temperature is -20 degrees centigrade. This at lower temperature evaporator runs and in this condenser runs at 40 degrees centigrade. That means this temperature is 40 degrees centigrade. TH is 40 degrees centigrade, right? The refrigerant enters the condenser as saturated vapor. This is given in question. Refrigerant enters the condenser as saturated vapor. That is point 2. This is the entry point of refrigerant in condenser. So this point 2 lies on the saturated vapor curve. So refrigerant enters the condenser as saturated vapor, right, and leaves as saturated liquid. And at an exit of this condenser, the state of refrigerant is saturated liquid. That means point 3 lies on saturated liquid curve, right? So this is the state of refrigerant at an entry and exit of condenser. The enthalpy and entropy values at saturated liquid and saturated vapor at this temperature. This is temperature -20 degrees centigrade and 40 degrees centigrade. This lower temperature and at higher temperature, this enthalpy and entropy are given, right? Then we have to find this UP of cycle and this refrigerant circulation rate is given. So given in this condition, we have to find the refrigerant capacity, right? So this is the VC cycle on TS plot and pH plot. Since it is given that the refrigerant enters the condenser as saturated vapor state, right? So it says it is given as refrigerant enters the condenser in saturated vapor state. So this point, in this condition we have changed some slight notation. This point 1 is taken as the entry of this point may be changed, right? This point might be changed as per your convenience. So in this condition, this point 1 is the entry point of this condenser, point 2 is the exit point of condenser, point 3 is the exit point of throttler, and point 4 is the exit point of evaporator. That means compressor is installed between 4 and 1, condenser is installed between 1 and 2, throttler is installed between 2 and 3, and evaporator is installed between 3 and 4. Okay, so this notation is slightly changed, so there should not be any confusion in this one. So this, first of all, be careful state. In this refrigerant enters the condenser as saturated vapor, so that's why this point 1 lies on this saturated vapor point. So this point 1, this lies on saturated vapor curve, right? This refrigerant exit the condenser in saturated liquid state. This point 2 lies on saturated liquid state. So point 2 will lie on saturated liquid curve, right? This H1, we know that this at 40 degrees centigrade. What is at 40 degrees centigrade? The TH. At TH, this Hg is given. Hg at what is the enthalpy at 1? This is H1. What is H1? H1 is the Hg at 40 degrees centigrade. Because 40 degrees centigrade, this is TH, higher temperature. This is the condenser temperature. Condenser works on that temperature. Therefore, this Hg is Hg at 40 degrees centigrade. H1 is Hg at 40 degrees centigrade. This is given just as per table. So you can see that at 40 degrees centigrade, the Hg is 200. This Hg is 200 kilojoule per kg. This H2 is what? This state is, this point lies on saturated liquid curve. Therefore, this H2 is equal to HF at 40 degrees centigrade. HF at 40 degrees centigrade. So go to this table. 40 degree HF. HF at 40 degrees centigrade. This is 80 kilojoule per kg. So this is H2 is equal to HF at 40 degrees centigrade. This is 80 kilojoule per kg. This value has been taken from this given data. Okay, given table. And we know this S3 is equal to S2 because this point 2 to 3 is the throttling process. In this condition, this enthalpy will remain constant. Therefore, S3 is equal to S2. This is equal to 80 kilojoule per kg, right? So, right. Now I have to find these values. So, first of all, in this problem, we need to calculate this H1 is given, S2 is given, S3 we have calculated. So we need to find out H4, enthalpy at an exit of evaporator or enthalpy at an entry of compressor. So for finding H4, we need to calculate dryness fraction at point 4 because this is very important. Unless we have this dryness fraction, we cannot calculate the enthalpy at point 4. So first of all, we need to calculate the dryness fraction at point 4. So how will we calculate? Right. The process 4 to 1. 4 to 1 is isentropic compression process. In this process, entropy remains constant, right? So therefore, S1 is equal to S4. The S1 is equal to S4 because process 1 to 4 to 1 is the isentropic compression process. In this process, this entropy will remain constant. So H1 is equal to S1 is equal to S4. We know this as what is S1? S1 is the entropy at this is SG. The point 1 lies at saturated vapor point, saturated vapor curve. That's when this S1 is equal to SG at 40 degrees centigrade. So come in the table. SG at 40 degrees centigrade. This is 0.67. So this is S1. So S1 is, what is S1? S1 is equal to SG at 40 degrees centigrade because this point lies on the saturated vapor curve. So S1 is equal to SG at 40 centigrade. Okay, this value is given this 0.67. Okay, as per this table, and this S1 is equal to S4. We know this S4. This point 4 lies in wet zone. We have the formula S4 is equal to SF plus X4 into SFG. Okay, this S4 is equal to SF plus X4 into SFG, and SFG can be written SG minus SF. And remember, this 0.4, basically this 0.4 lies on this lower temperature. Therefore, this S4 is equal to SF plus X4 into SGF at minus 20 degrees centigrade, right? This is at minus 20 degrees centigrade. This value, the SG is given 0.67, SF minus 20 centigrade, SF. Minus 20 centigrade, this SF is 0.07, this is 0.07, right? 0.07. X4 we have to calculate, and SG and SF at minus 20. From this table, look, minus 20 SG 0.7366, SF is 0.07. So in this condition, this simply we have to put this value SG and SF. This is 0.7366 minus 0.07, and from this value, this X4 is calculated. X4 is equal to 0.9. So this dryness fraction of refrigerant at an exit of evaporator, we have calculated this is 0.9, and this is equal to, so since we have calculated the dryness fraction at 0.4, we can calculate H4, enthalpy at 0.4. The H4 is equal to HF plus X4 HFG. This is at minus 20 degrees centigrade because this is the condition of this evaporator, and evaporator runs at lower temperature, right? So this H4 is equal to HF plus X4 into HFG. This is HF, this is minus 20 degrees centigrade. HF is, look at this table, minus 20, this HF is 20, right? This is 20 plus X4 is 0.9, and HFG, HG minus HF, minus 20, HG and HF, minus 20, this HG 180 kilojoule per kg, HF is 20. Simply we have to put this value. From where we can calculate value of H4. This H4 is equal to 164 kilojoule per kg. So this is the enthalpy at an exit of evaporator or enthalpy at an entry of compressor. So we have all these values, H1, H2, H3 and H4. Now we have to find, you can calculate the COP cycle. COP is equal to RE by work input. RE is equal to, you know, this S3 minus H4, because this evaporator is installed between 4 and 3. Therefore this H4 minus H3, and work input, this is required to run the compressor. This compressor is installed between 4 and 1. Therefore this work input is equal to H1 minus H4. Simply we have to put this value H1, H2, H1, S3 and H4. You will find this COP is equal to 2.33. Now I have to find refrigerant capacity in kilowatt. Since we have to find refrigeration capacity in kilowatt, in this condition we'll require to mass flow rate of refrigerant, because this is equal to m dot into H4 minus S3, right? The refrigeration capacity. So m dot is this is given in question 0.025 kilojoule, this is kg per second, and H4 is 164 kilojoule per kg, S3 is 80 kilojoule per kg. By putting this value, we can find out the refrigeration capacity in kilowatt. This is 2.1 kilowatt, right? So the session is just to stop here. We'll discuss next problem in next session. Thank you very much.